So he invited me to come, okay? And I said I had nothing to say, and he said I should come anyway. And then I said, I really will say nothing. And then he said, say what you said last time, which was a little bit problematic because I don't remember what I said last time. But last time, yeah, so the last time I spoke about this was to a meeting on the operation concepts. It was in Garching. So those of you who were there, I apologize because you're just going to hear the same thing again, more or less. But being in Florence, you cannot, well, I don't know, maybe you have, but you cannot not go to the museum, the Galileo Museum or whatever it's called. And as you can see, I just took a picture with my cell phone. But the critical component in this is the telescope come in many, many sizes. And in fact, even going back then, the top one is actually an octagonal telescope. Why on earth anybody would actually choose to make an octagonal telescope, I don't know. But the other fascinating picture is this one, which is an early telescope, which comes with these pieces, which will pretend are wavefront sensors and are actually described as accessories. So yeah, we're doing well. So those are the local color slides, so that you don't feel it's exactly the same presentation. As you can see, I've made an effort. I actually paid the entrance for the museum, so I think I've contributed to the local economy to the maximum possible. I think this evening we'll be contributing even more. So a few words about the telescope. The ELT is difficult. Okay, it's got a lot of stuff in it. Okay, now we can actually make it harder by making it complicated. It isn't complicated. Okay, and this is super important when you're thinking about it. If you insist it's complicated, you can mess it up very easily because it has more parameter space available to play with than you have sensing capabilities. So the only way you survive in this game at this point, before it is instantiated as a system, once it's instantiated, you can actually determine its properties and decide how you're going to work around that. But today, if you decide to go complicated, you will drown. So it is wrong to refer to this as a complicated system, and I don't. Okay? So if you can't keep this simple and make it work, then you're going to drown. So this is primary for us, okay? So our control strategy is to bring this thing into what I call a disciplined state in as simple a manner as possible, and then deal with derivative problems, okay? If you're not on the linear part of this, and you're already playing in complicated land, okay, you're not going to make it. Not for the basic system. Not today, okay? For the primary reason that we don't know where the problems will appear. So you can spend a colossal amount of time answering questions that you don't understand. Okay? So this is not necessarily the right path to follow. Okay? Now, the other thing is that this is an imaging telescope. And this, to you guys, maybe doesn't, you go, duh, why is he telling us this? Okay? But there's a fundamental property of an imaging telescope as opposed to an astrometric telescope. Okay? An astrometric telescope puts the stars in certain places. An imaging telescope makes small stars. These are orthogonal properties in how you control the telescope and how you design it. Okay? So astrometric properties are going to come out of this as derivative terms, as things that if it behaves well, it will have decent astrometric behavior. But it's been designed from scratch to make small stars. And this, again, matters when you're thinking about how you're maneuvering in its parameter space. We want to rely upon the, I don't know, Gerard, tell me how many years of adaptive optics experience can we say the astronomical community has? 30, okay. So there's 30 years of collective experience amongst many, many people on many telescopes with deep understanding and deep traumas as well. Okay? The problems that have been solved. Somebody this morning, yesterday said that we're technology driven. I think it was you. We're at the limit of technology continuously. So we're chasing. One of the most fascinating things up to now, I have not heard anybody chasing RTCs any longer. Okay? It is there, but it's not the thing that was always what was being chased, a few decades ago. Okay? There are other things. So up to now, your depth of experience has been in working in the linear perturbation regime. Okay? Your telescopes have been pretty good. Okay? This is where the deep experience comes. Okay? So what we're trying to do, I know this sounds kind of didactic and philosophical, but it actually matters to me very much, is that we work in a space where people's experience applies. And we don't chase things we don't really know until the telescope is instantiated. Once the telescope is instantiated, go crazy. It's a machine. It will do certain things and it won't do other things. But today, okay, we have to try and see if we can get into this robust space where we know what to do. Okay? And we have to be careful because outside this space, there be dragons. Okay? We don't know what is out there. Okay? You can't say, oh, my simulation showed that. Because 99.9% of all the simulations that one sees are actually parameterized and based on prior experience. So this is how I know to simulate this system. This is how I know the physics works. One of the reasons why at this stage I'd be very much against going to machine learning is that machine learning is the best way to build a robust function to go from a set of inputs to a set of outputs. It is unbelievably robust. It will always give you an answer, but it doesn't give you an understanding of where you went wrong. So when you're actually in operation, it is a fantastic tool for doing better. But if you want to design a system and you start with ignorance, you don't know your correlated errors, and you will get lost in the correlated errors. So you have to be careful. It doesn't mean it's not a fantastic tool. It has applicability and non-applicability. So where there be dragons, and since Roberto told us all about Jupiter, okay, so this is the island of Dia. It's just off the coast of Crete. And that used to be a dragon. And Zeus slayed that dragon and made it into a stone island. So you be careful about the Greek. So I'm going to have 2 more slides, and then I have 1,000 slides about other things, but or maybe 3 slides, but I'm not going to show the 1,000 slides because I think one of the things that I'm trying to do here is actually sit and answer any questions that people have. So the less I talk, the more chance you have to ask questions. But let me just give you a feeling of what the telescope that works. Okay? This is once we have actually gotten it to be as good as it can be. Okay? This is not the telescope that I get. This is a telescope that you get afterwards. Okay? So this is the back structure deformation of the primary. Okay? So the peak to valley is in millimeters. Okay? Okay? The movement of the image, okay, as the telescope inclines over. Okay? So to fix a lot of these, we have edge sensors, we have warping harnesses. Don't worry, I have lots of slides about that if you really want to know, but that's okay. Okay? We can fix that. What we can't fix is the wind on M1. Yeah, if we could, you wouldn't have that. Okay? So That's a few microns of peak to valley, but we hope it is reasonably low spatial frequencies. Okay? So that, a bit like dome seeing, should not be a real problem given that we have this super powerful M4. Unless it goes to high spatial frequencies or something really nasty, this should be okay. Yeah? And this is what you will be faced with. And then, since somebody brought up vibrations, the easiest way not to have vibrations is not to have sources that create vibrations. Okay? The telescope by itself, if you switch everything off, doesn't do anything. Okay? That is the cryocooler on the lasers. I'm happy without lasers, folks. I mean, I really am happy without lasers. I'm also happy without lasers. But that is a 1 Newton. You want to try 1 Newton, take your credit card out and let it drop on your hand. Okay? That's 1 Newton. Okay? Okay? So that's a 1 Newton shock at the edge of the thing. The amplitude is relatively small. Okay. So there's a talk at the end of today, I think, by Thomas Fromer. Oh, it says on Wednesday. Today must be Wednesday.
No, it's today evening.
Well, isn't today Wednesday? It's Tuesday. Excellent. Shall I fix it now? Okay. Thomas will tell you about this machine, which is the PHI station, the PDS, Phasing and Diagnostic Station. But to get the telescope into the state that you saw, okay, what we will receive is a jumble of glass. Okay? And to collect that, we need colossal stroke. Okay? Not only in the actuators, but also in the sensing. Okay? It doesn't come naturally. Your telescope, when you go to the VLT, that was not how it came out of the box. Trust me. Okay? If you ever seen a 1 arc minute star, okay, made like a piece of string, that's what comes out of the box. Okay? Not a round thing of a few arc seconds. So we need to collect all of this to get it to the state that you can use, okay? And it is a stage process. So again, there's a bunch of wavefront sensors, etc., that will come into this, okay? It's incremental robustness, okay? So you have to be able to do things again and again before you can get to the point where you start being clever with wavefront sensors, okay? And there's a third degree of repurposing of wavefront space. As you actually get into a more robust configuration, then you can actually gain back things. Okay, so I have, no, I'll skip that one. I have 2 slides. I don't know if you want to go through this. These are about how you use the telescope once you go into the normal mode. And there's quite a lot of discussion from various people of what would I do, and I think this is what you would like me to talk about. Okay. So this sounds very simple, but it's actually quite important that everybody understands that this is all the telescope does. Okay? You can go from here to there, okay? And then you stay there for a while. Okay? And then from where you are, you move around. Okay? Now, all of this sounds inane, but you actually have to appreciate that in our interaction between the telescope and the instruments, in this configuration, the sensing of the wavefront at the science level is done by the instrument and not by the telescope. So you have to understand this is what you do. Okay? The functionality the telescope gives you is to follow a source, follow somewhere, and to move around. Yeah? So when we preset, what the telescope will do is go somewhere, set up on its guide stars, okay, and will actually fix M1 and M2 and M4 such that you have a decent wavefront. Yeah? Everybody kind of happy with that? That should be fine, okay? The reason we go to a fairly decent wavefront is that that maximizes the stroke available for you guys to do adaptive optics. That gets you into the linear perturbation regime. You're chasing atmosphere plus this perturbation of the primary, but that's it. That's what you're chasing. And our job on the telescope side is to make sure you always have stroke. Yeah? So that you are never running out of stroke. Yeah? You may temporarily saturate because you've gone a little bit too far or not, but that's actually not a genuine running out of stroke. You haven't reached the mirror to the limit. This instantiation is not good. There's a very big difference between a command that is bad and the mirror having reached, the whole mirror having reached its limits. Okay? So, once we're observing, the instrument wavefront sensor takes over, so we do a handover, okay? You guys take over. Where do you take over about? Okay? You take over about the last position of the M4. Okay? That is your 0. I don't like calling it flat. It is not flat, but that is your 0. Okay? Around this 0, you should have the microns of stroke that is necessary, otherwise we have not cleaned up. And then you're just running a one actuator problem. It's exactly as if you're sitting on the VLT with one DM. You can then put more DMs if you like, or not more DMs, you can do whatever you like, but you actually are running a one DM. If you're doing SCOW, you're running a one DM system. Okay? The telescope lets go at that point. Its guide probes are no longer involved in control. It's all yours. Okay? This matters. We are watching, but we're not controlling. Okay? So if we can get this to work this way, which will depend on hysteresis, will depend on the instantiated system, etc., etc. But the simulations say we can, but until we do, okay? Then everybody's in happy land. Okay? There's no reason to complicate it beyond this. Okay? So my statement to all of the AO community in general, this is one flavor of it or whatever, is this is the path we're going to go down. When we fail, yeah, I'm not saying, that it's guaranteed that it will work, etc., etc. Then we will know which problem to solve. Now, the question is, do we have the sensing capacity to address those issues? That is the question. Not how will we solve virtual problems that are based on other traumas. Is will we have that sensing capacity? So this is observing. I have one slide, I think, about, that's the same, makes no difference. Whether you're controlling or I'm controlling makes no difference to the system. We're working through exactly the same interface. There's no difference. There's no prior knowledge that the telescope is using in its sensing. And Thomas, with the whole of the phasing station, has to comply with the same interfaces that everybody else has. Okay, so I think it's my last slide. Offsetting. Okay, and this slide repeats 3 or 4 times, but I want to take a few minutes in offsetting because this is the case where there's a lot of conversation. So you have control now, and now we're going to offset and go back and forth. Okay. So I have 3 cases, but I want maybe I move the slides, but they're basically the same thing. Let's pretend you want to do a 5 milliarc second offset. Yeah, I don't care why, but let's say you want to do a 5 milliarc second offset. You could say, I'm going to open my loops, tell the telescope to move by 5 milliarc seconds, and then reclose my loops. So I can promise you what the telescope will do if you tell it to move 5 milliarc seconds is nothing. Okay? It won't move. It literally will not move. Okay? It is not a different position in its dead bands. So that is not how we would move 5 milliarc seconds. Probably you just change your slope reference and the whole thing would move a bit. This would end up being a bit more tilt on M4, which if you did it many times, we would offload onto M5 and out into the system. Okay? But that's how you would do this. You possibly wouldn't even open your loops. Okay? If it was a 5 milliarc second offset, you possibly would just nudge it and it would go. You could have the other one, which is, I don't know, 5 arc seconds. You can pick these numbers as you like, 10, whatever, where you could say, well, I don't want to be nudging it by 5 mass as I go along to get to where I want. So I'll open my loops, move by 5 arc seconds, and reclose. Now, would you do this by giving the telescope all the way back to me and then retaking it from me? Or would you just move either your field selector, your guide probe by 5 arc seconds, your aperture, whatever, and try and close again? Yeah, that's the second scenario is what I would plan to commission, and if it doesn't work, then we have to do something else. In which case, nothing has happened either. Okay? As far as the telescope's concerned, okay, the only thing is that you have to tell me that you've changed your array and deck because it's better than dragging me around in the wrong place, but nothing has happened. Okay? And this basically goes out to whether you want to go 100 arc seconds away. As long as you have a guide star, you can get your guide star, then you're in charge. And this is a simple system. Okay? There are minor cases where you say, I want to go there and I don't want to have a guide star. Can you take over? That's perfectly okay. You can say, I want to go there and then I want to go back to where I was before. None of those are any different to the scenarios that I've described up to now. Okay? So there isn't anything magic in this. Okay? The only question is, do we know how to handle the handover? Okay? And today, we believe that we can do this in control theory. There's something called bumpless, where you transition one from the other, and we're doing it bumpful. Okay? So we let go and you close. Okay? And that is the cleanest way of doing it, because that does not create any interface between the two sides that needs to be checked. There's no prior knowledge. You just close. So if we can get this system in that configuration, then it is actually a straightforward problem to address. So this is how we plan to go. Okay? And if it doesn't work, then we'll see what to do. So that's the end of, I have, I think, 700 other slides, which are actually content full, but not necessarily for reading. Anyway, so that's all I wanted to say.